The derivative can not only determine slope, but it can determine the rate of change of one variable with respect to another. Some rate of change applications include population growth rates, production rates, water flow rates, velocity, acceleration, motion of an object moving in a straight line, and eventually we'll get to motion of an object moving along a curve. If the motion of the object is up or to the right, then that means it's going in a positive direction. But if it happens to be down or to the left, that means it's going in a negative direction. The function that gives the position relative to the origin of an object as a function of time is the position function. The object changes its position by the amount of delta s over a period of time delta t. Using the formula for average speed, rate equals distance over time, we can find a formula for average velocity. So what I remember is distance equals rate times time. And so if we were to solve for the rate, we would divide by t, and we get distance over time. That's speed, right? The distance over time. 60 miles in 1 hour is 60 miles per hour. The average velocity can be found by the change in distance over the change in time. So delta s over delta t. Delta s is a function of t. So if it helps you, you can think of it as s of t. The average rate of change is s of t plus delta t minus s of t over delta t. That would be our average velocity, which is almost equivalent to average speed, except velocity gives a direction. It gives a little bit more information than speed. If your average velocity turns out to be negative, that doesn't mean that you're going negative 10 miles per hour. That doesn't even make sense. That signifies the direction. And that's why this is important to give us more information about the problem. Find the average velocity over each of the following time intervals. If a billiard ball, that's from a pool table, is dropped from a height of 100 feet, its height, s, in feet at time t, in seconds, is given by the position function s equals negative 16t squared plus 100. So we need to find the average velocity over the following intervals. They want to know the position, the change in position over the change in time. The change in time here is from 1 second to 2 seconds. So the change from 1 to 2 is 1. You added 1 second. So 1 is delta t. The change in time is 1 second. Delta s over delta t is equal to the function of, t is the time we start with, so 1 plus 1 minus s of 1 over delta t. This is just rate of change, slope formula. So to find the change in velocity over this interval, we need to take the position of the object at 2 seconds, subtract the position of the object at 1 second, and then divide it by the change in time. Hey, we actually knew the change in time this whole time. It's 1 second. I'm not going to put that S so that we don't get confused. Okay, so S of 2 minus S of 1, that's going to be my change in velocity. Okay, so here is the S function. Plug in 2 and then plug in 1. S. So we plug in 2 into the position function, and then we subtract and plug in 1 into the position function. Now we just have some algebra to do. Negative 48 over 1. Now the position function was talking about the position in feet at time t in seconds. So feet per second will be our units. Negative 48 feet per second. And the negative indicates that the billiard ball is falling, which makes sense because if you fall, gravity exists. Let me show you one other way that you could think about this if this plugging in was a little bit confusing to you. I'm just going to start off B. I'm not going to do the whole entire problem so that we can get to regular velocity. This is just average velocity so far. But I would say T is your starting time, and delta T is the distance between the starting time and the ending time. So delta T would equal 0.5. Okay, that's the way that we did it in part A. But if it helps you, you say these are the intervals of time, right? These are values of T. So T is 1, and then T is also 1.5. So all you need to do is plug in 1 into the position function, and then to plug in 1.5 into the position function. This one was 84 from part A. When you plug in 1.5 into the position function, you end up getting 64. So if you took the slope between these 2 points, I would say 64 minus 84, the change in S over the change in T, 1.5 minus 1, you would get 20 over 0.5, and that would be negative 40 feet per second. If this is an easier way for you to understand it than plugging it into the exact formula, that's totally fine. Velocity. Instantaneous velocity is literally velocity. Okay, so what we were talking about the entire time before was average velocity. This is instantaneous velocity. How does your car know exactly how fast you're going within 1 instant? Speed is distance over time. So how do you know it instantaneously? Well, I bet it has something to do with the derivative. Okay, so the way to find instantaneous velocity is to take the limit as delta t approaches 0 of average velocity. The formula from the last page. So S of t plus delta t minus S of t over delta t. This is just another way of saying, hey, the derivative of the position function. The limit of this expression is the formula to find velocity. This would be that v of t is equal to the derivative of the position function. So velocity is the derivative of the position function. You may remember the position function from our problems with velocity before, Remember that v sub 0 is initial velocity, s sub 0 is the initial position, and g is gravity. Obviously, gravity affects falling objects. And gravity for meters is 9.8 meters per second, and the pull of gravity in the unit of feet is 32 feet per second. So our example here, at time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. The position of the diver s at time t is given by the position function here. When does the diver hit the water, and what is the diver's velocity upon impact? The platform is 32 feet above the water. That means the ground, or the water, is at 0, okay, your x-axis. We want to know at what values of time is the position of the object 0? Is the position of the object on the ground or in the water? We'll divide both sides by -16. You don't have to, but it just makes it so I don't have to worry about that coefficient. And now we'll factor. You could have 2 and 1, and it's -2 and +1. So the time could be +2 seconds, or the time could be -1 second. What do you think makes more sense when the diver hits the water? After they've jumped, are they going to hit the water in -1 second or 2 seconds? Well, that's pretty obvious. So they're going to hit the water in 2 seconds. Perfect. What is the diver's velocity at the time of impact? The time of impact is t equals 2. Velocity is the derivative of the position function. So you need to find the derivative of the position function and then plug in the value t equals 2. This is a polynomial, so I can use the power rule. Yay! So to find the derivative of s with respect to t, pop down, power down. 2 times -16 is -32 times t, and then you will subtract 1 from the exponent, so t to the 1, plus. Remember, the derivative of t is 1, so 16 times 1, plus the derivative of a constant is always 0. S prime of t is equal to -32t plus 16. We started off with a parabola. The derivative is a line. That makes sense from graphing a derivative. And now you need to find s prime of 2. So what is the velocity after 2 seconds? Because 2 seconds is when the diver hits the water. Plug in 2. -48 feet per second. That's velocity.